In this video, we're going to cover section 1.17.2, heterogeneous catalysis. Heterogeneous catalysts are extremely important in industrial chemistry. The vast majority of industrial catalysts are solids. For example, the Haber-Bosch process for the production of ammonia from hydrogen and nitrogen is catalyzed using iron, as shown here. This is an example of heterogeneous catalysis because the reactants and product are in the gas phase, but the catalyst is a solid. So the phases are different. An important step in reactions involving solid catalysis is the adsorption of one or more of the reactants to the solid surface. The first assumption is that the particles, i.e. the reactants, adsorb to the surface without changing their internal bonding, a process referred to as physisorption. A dynamic equilibrium exists between the free and surface adsorbed species, also known as the adsorbate, and information regarding the kinetics of surface adsorption and desorption can be obtained by studying this equilibrium as a function of reactant pressure over the surface of the catalyst. A critical parameter in evaluating surface adsorption is the fractional coverage, given as theta. And this is defined as the number of adsorption sites occupied over the total number of adsorption sites available. So if we had a theta equal to 0.90, that would be like saying for 100 adsorption sites, 90 of those would be occupied. The fractional coverage can also be defined in terms of a volume, V adsorbed over V subscript M, where V adsorbed is the volume of adsorbate at a specific pressure, and V subscript M is the volume of adsorbate in the high pressure limit corresponding to a monolayer coverage. So studies of adsorption involve measuring the extent of adsorption, or theta, as a function of reactant gas pressure at a specific temperature. The variation in theta with pressure at fixed temperature is called an absorption isotherm. The simplest kinetic model describing the adsorption process is known as the Langmuir model, where adsorption is described by the following mechanism, where R is the reagent or reactant in the gas phase, M is the unoccupied adsorption site on the surface of a catalyst, and Rm represents an occupied adsorption site. The rate constants, K1 represents the rate constant for adsorption, and K-1 represents the rate constant for desorption. So what's shown in this figure is an example of an adsorption isotherm, specifically the Langmuir isotherm, where we're plotting the fractional coverage, theta, against the pressure of the reagent in the gaseous form. And for each of these curves, there's a number associated with the equilibrium constant, which in this older version of your text refers to alpha. We'll refer to it as equilibrium constant, uppercase K, which we know from previous examples is a ratio of the rate constants for this equilibrium. And so as the equilibrium constant increases in value, what that is effectively saying is that adsorption, the rate constant for adsorption, is larger in magnitude than the rate constant for desorption. In that scenario, we see that we have almost complete coverage at very low pressures. Whereas if the opposite is true, that is, the magnitude of desorption is greater than the magnitude of the adsorption rate constant, as shown in this example, this means that it takes quite a bit larger pressure of the reagent gas in order to get to that complete coverage, fractional coverage close to 1. So there is a direct correlation between the equilibrium constant and the pressure required to achieve a fractional coverage equal to 1. 3 approximations are used in the Langmuir model. First, all adsorption sites are equivalent and the surface is uniform. Second, adsorption and desorption are uncooperative processes. This means that the occupancy state of the adsorption site will not affect the probability of adsorption or desorption for adjacent sites. And third, adsorption is complete once monolayer coverage has been reached. With these approximations, the rate of change in theta will depend on the rate constant for adsorption, K1, reagent pressure, P, and the number of vacant sites, which is equal to the total number of adsorption sites, N, times the fraction of sites that are open, which is given by 1 minus theta. As a result, we can write for this change in theta with time, it's going to be equal to the product of those 4 specific terms. Now, the corresponding change in theta due to desorption, it's related to the rate constant for desorption, K minus 1, and the number of occupied adsorption sites, which is given by the total number of adsorption sites times theta, which is the fractional coverage. And so this would be the second term associated with this changing theta with time. At equilibrium, the change in fractional coverage with time is equal to 0. So we can set the sum of these 2 terms equal to 0, similar to what we've seen previously for systems at equilibrium. So with this expression, we can rearrange it for theta. So we can bring like terms together, those terms associated with theta to one side of our equality sign and the others to the right. And then we can divide through. And so we end up with a final expression for theta. Now note, this expression shows explicitly the adsorption rate constant and desorption rate constant. We can also divide each term by K minus 1 such that we can now include the equilibrium constant. So if we divide this term and this term by K minus 1, we end up with the equilibrium constant times the pressure. And of course, this term will end up being 1. So the equilibrium constant, again, defined as the ratio of those 2 rate constants. So this is the equation for the Langmuir isotherm. So as we'll see in one moment, the reciprocal of the Langmuir equation allows one to determine the volume corresponding to complete coverage, and we'll see that in just a second, and the equilibrium constant for adsorption desorption, which you can see now. Now we can multiply both sides of the Langmuir equation by Kp plus 1. That gives us this expression. If we were to substitute theta with V adsorbed over Vm, we have this expression. And now if we divide both sides by the product of V adsorbed and the equilibrium constant, we end up with this expression. And then we can rearrange this expression into 2 final forms, which basically give us linearized equations of the Langmuir equation. So for the Langmuir isotherm to be consistent with experiment, a good linear fit to the experimental data will be observed for a plot of the ratio of the pressure over V absorbed against pressure, if there is a strong association between these 2 variables. The slope and y-intercept of this linear fit gives a measure of Vm and the equilibrium constant. So if we go back to our expression, the slope is equal to 1 over Vm, and the y-intercept is equal to 1 over kVm. So if we determine the slope and the y-intercept, and we divide the y-intercept by the slope, we'll end up with 1 over k. And so the inverse of that would give us the equilibrium constant. So as shown previously, this figure presents Langmuir isotherms for various values of the equilibrium constant. And notice that as the rate constant for desorption increases relative to adsorption, higher pressures must be employed to reach a theta equal to 1. So as the equilibrium constant gets smaller in value, we need to increase the pressure further to reach a fractional coverage approaching 1. This behavior can be understood based on the competition between the kinetics for adsorption and desorption. Correspondingly, if the rate constant for desorption is small, the coverage becomes independent of pressure for lower values of pressure, meaning that as the equilibrium constant increases in value, we're going to observe a fractional coverage of 1 at much lower pressures than we would observe if the equilibrium constant was much smaller. So often, adsorption is accompanied by dissociation of the adsorbate, a process that is referred to as chemisorption and described by the following mechanism. So in this scenario, we have a molecule R2 in the gaseous form, which adsorbs to the surface with dissociation to give 2 R fragments on the surface. And the rate of adsorption is proportional to the pressure and to the square of the number of vacant sites, because 2 sites are needed to accommodate the 2 fragments. So think of it as a molecule like H2 being adsorbed to a surface. Upon that adsorption, the molecule itself will dissociate into 2 hydrogen atoms, each occupying a site on the catalytic surface. So the rate of change of the fractional coverage due to adsorption is then equal to the product of the rate constant for adsorption, the pressure, but now we have this squared term associated with the fact that 2 fragments are adsorbing to the surface for every adsorbate, R2. Desorption also requires that 2 R fragments encounter one another so they can leave as R2. And so the rate of change of the fractional coverage is therefore second order in the number of sites occupied. And that's shown in this expression here. So again, these will represent the 2 terms associated with the change in theta with time for this type of adsorption, which we refer to as chemisorption. So at equilibrium, the change in fractional coverage with time is equal to 0. So again, we can write the sum of those 2 terms equating that to 0. And now we will rearrange this expression for theta. And so again, we'll take like terms over to one side, all the terms containing theta. We can introduce the equilibrium constant for the ratio of K1 over K minus 1. So we're left with that being equal to 1 over the product of the equilibrium constant and pressure. And then we do a few rearrangements until we end up with this particular form of the expression, 1 over theta being equal to 1 plus 1 over the square root of Kp. So if we continue along this derivation, when we get to this point, we'll take a common denominator. That gives us this expression. And then finally, we can invert both sides to express theta as a ratio of the square root of Kp over the same square root of Kp plus 1. So this is the equation for the Langmuir isotherm for adsorption with dissociation. The previous Langmuir isotherm that we presented was for a non-dissociative mechanism. This is the example for dissociation. So one takeaway for the Langmuir isotherm for adsorption with dissociation is that surface coverage depends more weakly on pressure than it does for the non-dissociative adsorption. And that's shown with this square root term for pressure when equated to our fractional coverage. So the shapes of the Langmuir isotherms without and with dissociation are shown below. So without dissociation, we're referring to physisorption, and with dissociation, we're referring to chemisorption. You can see that the fractional coverage increases with increasing pressure for both and approaches theta equal to 1 only at very high pressures when the gas is forced onto every available site of the surface. So when we compare the Langmuir isotherms without dissociation, the non-dissociative adsorption, to that of isotherms with dissociation or the dissociative adsorption, we can clearly see how the fractional coverage differs at different pressures for the same equilibrium constant. So when the equilibrium constant is 10, for physisorption, we're going to reach fractional coverage at much lower pressures than for chemisorption, where even upwards of 10 atmospheres, we still haven't reached a fractional coverage of 1. Now, the assumptions employed in the Langmuir model may not be rigorously obeyed in real heterogeneous systems. And this is for a few reasons. One, surfaces are generally not uniform, resulting in the presence of more than one type of adsorption site. Two, the rate of adsorption and desorption may depend on the occupation state of nearby adsorption sites. And three, if the initial adsorbed layer can act as a substrate for further adsorption, then instead of the volume of gas adsorbed leveling off at high pressure to a value corresponding to a complete monolayer, it can be expected to rise indefinitely. As a result, deviations from the Langmuir isotherm are often observed, which has led to the development of new models to describe these heterogeneous catalytic systems. These include BET isotherms, Temkin isotherms, and Freundlich isotherms. But this is beyond what we want to cover as an introduction to heterogeneous catalysis. So if you have any questions about heterogeneous catalysis, please send me an email and we can carry on the discussion from there. Thank you.